Good day students, I am Dr. Smita Sharma and we were discussing differential amplifier. We had studied some numerical problems related to differential amplifier and we have learnt how to solve them. Now in this lecture we will study level translator. Now before studying level translator, we'll again see the block diagram of operational amplifier. So this is basic block diagram of an operational amplifier. Operational amplifier or op-amp is a direct coupled amplifier which is made up of one or more differential amplifiers followed by a level shifter as shown in the following block. So as we see in the diagram, this first stage is the input stage having two inputs, and it is basically a dual input balanced output differential amplifier. Then intermediate state consists of dual input unbalanced output differential amplifier. Then we have a constant current source and a level shifting stage, and then we have an output stage. So here we'll study level shifting stage. Before discussing level shifting stage, we'll discuss cascaded differential amplifier, because in the block diagram we had seen one differential amplifier stage is coupled to another differential amplifier stage. Now first of all we'll see how differential amplifiers can be cascaded. Now this is the diagram of cascaded differential amplifier. This is basically a two-stage differential amplifier. The first stage is dual input balanced output differential amplifier. See here, this is dual input and output is taken from both the ends, so it is a balanced output. The second stage is another differential amplifier driven by an output of the first differential amplifier. A single-ended output is taken from second stage, as you can see here. This is output is taken from here. So this is single-ended output. Both stages use the emitter bias technique, that is combination of RE and VE to set up emitter current in the differential pairs. Here again you can see here RE is given. It is similar to the first basic diagram of the differential amplifier that we had studied. In many cases, the matching of transistors and resistor values is essential for proper operation of the differential stages. For this, use of transistor array such as CA3086 is recommended, so that both the two transistors and their two stages are identical to each other. Now this is basic cascaded differential amplifier. Now we'll first go through one of the example what happens when a cascaded differential amplifier is used. So the example is, for the cascaded differential amplifier, determine the collector current and collector to emitter voltage for each transistor. And some these parameters are given and rest parameters are shown in the diagram. So first of all we want to calculate collector current and collector to emitter voltage for each transistor. Why we are calculating this? Because obviously it is asked, but these two values are the these two values are the operating points of the that are calculated in DC analysis, and they decides the operating Q point. To determine the collector current and collector to emitter voltage of transistors Q1 and Q2, we assume that inverting and non-inverting inputs are grounded. This thing we had studied in the DC analysis, that whenever we are doing DC analysis, we basically ground the inverting and non-inverting inputs. That is, signals are removed from it for DC analysis. And we already know that the equation that can be calculated is given by VEE minus VBE upon 2RE plus RIN upon beta DC. If we put the respective values, we get IE barabar 0.988 milliamperes. Now, because both the two stages are identical, so both the emitter currents will be equal, and because both the emitter currents are approximately equal to collector current, so IC1 and IC2 will be similar to 0.988 milliamperes. In the same way that we had calculated before, we will calculate the voltage between collector and emitter for Q1 and Q2. This will be calculated by a simple Kirchhoff's law equation that we had discussed in the DC analysis. By putting the respective values, it comes out to be 8.54 volts. Now we'll see what happens for Q3 and Q4. This numerical was simple that we had discussed in the previous lecture. Now we'll see what happens when we study Q3 and Q4. So again we are taking the same diagram. Next we will determine the collector current in Q3 and Q4 by writing the Kirchhoff's voltage equation for base emitter loop of the transistor. Now we'll be taking this loop starting from we'll start from here, go through here, and again here, and then here, and then here, and then here. So we'll write equation from VCC to minus VEE and following this path. Here, then we'll go here, then we'll go through the base to the emitter to resistor RE dash, then this resistor, and then minus VEE. So in this way we get this equation. When we put the respective value and calculate, we get IE3 equal to 0.569 milliamperes, which is again similar to IE4 because both the stages are considered to be identical. Next we calculate the voltage at the collector Q3 and Q4 in the same manner that we have calculated before. It comes out to be 9.32 volts. Next we calculate VCE3. VCE3 and VCE4, because both the transistors are taken almost identical, will be similar to VC3 minus VE3. By putting the respective values, we get VC3E3 is 2.2 volts. Now here it is to be seen that what we have calculated here, IE3, which is basically the operating point IC, which is equal to operating point IC, and VCE, which is second operating point in DC analysis. So finally what we get, Q1 and for Q1 and Q2, ICQ is 0.988 milliamperes, VCEQ is 8.545 volts. But for Q3 and Q4, ICQ is again 0.988 milliamperes and VCEQ is 8.54. VCEQ is 2.2 volts. No, not 2.2 volts. It is 9.32 volts. Now what we had seen here, that output terminal, at the fourth terminal the output collector voltage is not equal to that obtained at Q2 collector. It has risen. So basically what happened, we'll conclude, we'll first make the observation and then we'll conclude. So results of examples of cascaded differential amplifier. What were the observations? Because of direct coupling, the DC level at the emitters rises from stage to stage. We have taken only 2 stage and the collector voltage has risen. This increase in DC level tends to shift the operating point of the succeeding stages and therefore limits output voltage swing and may even distort the output signal. Because if the operating point shifts, the swing of the output signal also restricts, and if it swings, then it is obvious that signal will get distorted. The voltage at the output terminal of the second stage is well above ground, which also contributes to the errors in DC. So what do we conclude? Since op-amp uses direct coupling method, therefore DC voltage level at the emitter terminal rises from stage to stage. After some time, this cumulative voltage could be very disastrous. This exponentially increasing DC level tends to shift the operating point of the upcoming stages. Therefore, it becomes mandatory to limit the voltage swing, thereby protecting the output signal from distortion. So, it is mandatory for us to find a method to stop this increase, but we can't stop it, but we can reduce its effect by adding an additional circuit. This additional circuit is what we call level translator. So now what is level translator? Level translator or shifter is a circuit which can shift DC voltage level of a signal to 0 voltage. In other words, level shifter is a circuit which can eliminate DC voltage from a signal. It is designed to eliminate a single DC voltage. So what is this? Is basically a level shifter diagram. It is basically an emitter follower. What is a level shifter? It is basically an emitter follower with which a voltage divider is attached. What is voltage divider? This thing is voltage divider, because these two resistors divide the voltage and output is taken from here and the output reduces to 0. So a DC voltage at the base of transistor Q gives a 0 volt DC output. Hence it can be used for the R purpose in differential amplifier, in operational amplifier after the differential amplifier stages. Two more, it is basically dependent on R1 and R2. Now two more circuits. There are many circuits, but two more circuits can be named. One is emitter follower with constant current bias and second is emitter follower with current mirror. These two level translators are also capable of bringing the DC voltage to 0. Better results are obtained by using an emitter follower with diode constant current bias or a current mirror bias in place of voltage divider emitter follower. So thus we have seen what is a level translator and what is its circuit diagram. Now next, this completes our differential amplifier and the two things that are associated with the differential amplifier, that is level translator and constant current bias. Now we'll start the whole thing as a unit, that is basic operational amplifier, in the next lecture. So we'll again start what is an operational amplifier and what are the ICs that are used in basic operational amplifier and what are its applications. Thank you.